Going live, you are live.
Okay. So, good morning, students. We are today now going to explain or we are going to start the chapter of magnetic effect of current. We start the chapter of magnetic effect of current. So, as the terminology states that magnetic effect. So, we are not studying about the magnetism. We are not talking about magnetism. We are talking about the magnetic effect of current. Means, if there is a current passing through a conductor, then there will be a magnetic field which will be generated around the sides or around the surface surrounding the conductor. Okay. So over here, so basically, as I told you that in the chapter of in the syllabus of class 12, we are going to learn about electrostatics. Thereby, we are going to start with current electricity, and thereby we will go to magnetism. We are not teaching over here magnetism. Again, I repeat, we are not teaching over here as a magnetism. We are teaching over here the magnetic effect of current. That if current is flowing through a conductor, there will be a magnetic field produced. So here comes the interrelationship between magnetism. So we will come to this topic. We will come to this topic and we will go into the detailed part of this chapter in the next class. But we go a brief recap of the chapter of electrostatics we have done. And we are also going to explain a little bit of electrodynamics. Okay. So we are going to study a little bit of electrodynamics because this one is very, very important. This one is very, very important because the interrelationship has been started. So electrostatics is over. The current electricity is also got almost over. So we are now going to go into the interrelationship between the current and magnetism. That's how a current flowing through a conductor produces magnetism. So we further today is going to discuss a little bit of electrodynamics. So that will be helpful for you in the broad aspects. Okay. So to start with, I told you that basically Maxwell's laws are the basic fundamentals of electrodynamics. Okay, the Maxwell's laws are basic fundamentals of electrodynamics, and almost all the electrodynamics equations can be solved by the method of this Maxwell's law. In the class also, while I was taking the class, I told you a few Maxwell's equations that del E is equal to rho by epsilon naught. I had told this one that del dot E is equal to rho by epsilon naught. We have told this. Okay, and I had told this one also that this particular sign with a dot is said to be as what we are saying is divergence. The topic is not there in your syllabus, but since you have learned the Gauss's law, so this particular topic is going to enhance or broaden the concepts, how we are using the Gauss's law and how the Gauss's law is being used in electrodynamics. Okay. So this one I had told you that this dot E is equal to rho by epsilon naught. Another I had told that del cross E is equal to del E del E. And this one was said to be as curve. This one is said to be as a curve. Okay, and these are the two basic Maxwell's equations, and we had already discussed this one in the class also. That what is del cross E. Okay, so if we come back or a quick recap of the Gauss's theorem, what does that Gauss's theorem was saying? that this was the Gauss's theorem, what we had told, and again I repeat that was we are going a bit recap of the topics what we had got. That if Qin is the amount of the charge enclosed in a surface, as I told you, what is a closed surface? Empty pencil box is a closed surface because once the pencil box is being closed, if you want to come out of the pencil box, then you have to either break it up or you have to make some holes or you have to make some way out of the pencil box. So this one is the amount of the charge which is enclosed in a closed surface. E is the amount of the electric field and ds or dA is the small amount of the vector or the area vector. So if this one is the, suppose is a arbitrary surface, and if you are going to take a small particle here or a small area that is dA, and the dA vector goes like this. Suppose this one is the dA vector, and this one is the direction of the E. Then the Gauss's law states that E dot naught. This we have learned everywhere. Okay. And suppose I have taken a small area dA, and if I am taking this one to be as a small volume, suppose this one is a small volume, very small volume, very small volume, but obviously we are not going to consider that the volume is infinitely small or dV is tending to 0 and this and that, because this one is physics. So if this one is physics, we cannot take dV to be as so much small that it will be almost tending to 0. No, we are not saying this. At least we are going to assume there are 5,000 or 10,000 number of molecules which is able to present inside this volume. So if we are going to divide this one as integration E dot ds divided by dV is equal to Q enclosed by epsilon naught and dV. Okay, so I am dividing by this small volume. I am dividing by this small volume on both the left and the right sides. Then it is integration E dot ds by dV is equal to Q enclosed by epsilon naught into dV. Right? Okay. So Q enclosed is what? Is the amount of the charge which is enclosed in this small volume. Okay? And divided by dV will give you what? Will give you what? We will get the charge density. So even to get the charge density, that is rho divided by epsilon naught. Okay? So amount of the charge, or you can write this one as dQ in, because the charge which is enclosed in that small volume will be a very small amount of charge. So it is dQ divided by epsilon naught divided by dV. So dQ divided by dV will give you what? That is rho, that is the charge density. So this one is only the expression of divergence, that is del dot E is equal to rho by epsilon naught. Okay. Now we are going to go into the detail of this del dot E. That what do we understand by this very particular thing? Suppose okay, so we continue. We are increasing or we are explaining that very particular what the expression we had got, that is del dot E is equal to integration E dot ds divided by dV is equal to rho by epsilon naught. This one we had done. So I will preface that del dot E is equal to what? That the flux which is coming out of that very small volume divided by dV is equal to rho divided by epsilon naught. Okay. So right now I am doing a diagram and we are going to use the Gauss's theorem. So I am basically emphasizing the concepts of the Gauss's theorem. Okay. So suppose this one is the y-axis This one is z axis, and this one is the x axis. Suppose these are the three axes, and I am moving a very small distance, and this one is the suppose the origin, and I am moving a small distance along y axis, a small distance along z axis, and a small distance along x axis by a distance dx, dy, and dz. So I can frame a cube like this. I am framing a cube like this. Okay. So how many faces are there? There are 6 faces. One face, say face number 2, face number 3, face number 4, top ka face, and another is the bottom face. So there are 6 faces, and we are going to take out that what is the amount of the electric flux which is emerging out of this cube. And the particle has moved a distance, suppose dy in this direction, dx in this, and dz in this. Understood? So if I am going to take that, suppose I am drawing this x, y, and z axis like this way, such that this origin is having the coordinates x, y, z. Suppose this origin is having the coordinates x, y, z, and this coordinate will be simple x, y plus del y, z. I can write in this way. This coordinate. Again, this coordinate I can write out. Okay. So suppose I am taking the surfaces, this surface and this surface. Okay, I am taking these two surfaces, and suppose there will be an electric field over. I am going to draw a normal on this surface. This will be parallel to this y-axis, right? This will be parallel to this y-axis because I am taking this surface. Okay, so the normal to this surface, I am going to take the small surface out of here. Then the normal to this surface will be parallel to the y-axis. Okay, or what will be the value of dA over here? What will be the value of dA over here? Tell me what will be the value of dA over here? It is moving along which axis? Y-axis. So the displacement has taken place along y-axis. So this is the area. This one is the area. What is the area? This area is along x and along z. So it is dx dz along the positive y-axis. So it is plus j. Okay. Okay. So the area vector over here is dx into dz, and it is along the positive y-axis, so it is plus j. So if I am going to do this, the flux over here, then it is E dot dA. Suppose the surface is 1, I am taking the surface to be as 1. So that is equal to E dot ds, E dot ds or dA. So what is the E? E is Ex I cap plus Ey j cap plus Ez k cap in dot product of the dA. What is the dA over here? dA is dx dz. dx dz j cap. dx dz j cap. Right? Understood? Again I repeat. E over here is the electric field, and the electric field I have resolved into 3 components. One is Ex I cap, Ey j cap, Ez k cap. The area vector over here is Ex into dz, and it is parallel to the positive direction of the y-axis. So it is j cap. Okay, and the Flux along this surface is E dot dA. So it is Ax I cap Ey j cap plus Ez k cap, and the area vector was Ex dz into j cap. So it is Ey because I component and Z component will not be having the dot product, or it will be having the dot product to be as 0. So Ey x comma y plus del y comma z at this point, like into dz dx into j cap. So it is Ey at which point x y plus dy or del y, whatever you can write, dy if you want to write dy, and z into dz dx j cap. Okay. Now if I come to this surface, the surface opposite to this one, okay, in which direction the dA vector will be? In this direction the dA vector will be, right? In this direction the dA vector will be, and the dA vector is opposite, or it is along the negative y-axis. It is along the negative y-axis. Clear? In this surface, the normal if I am going to put, or normal if I am going to draw, it is along the negative y-axis. So dA is equal to dx dz into minus j cap. So if this one is equation number 1, we can write E dA2 equal to Ey, and this Ey is taking place at which coordinate? At this coordinate. What is the coordinate over here? Y. Here the coordinate was y plus del y. Here the coordinate is y, right? So the coordinate to be over here is x, comma y, comma z, dx dz, and minus j cap. This is equation number 2. Are the things clear? Are the things clear? Is it clear to everybody? So see, again I repeat the thing. Electric vector is being resolved into 3 components: Ex I cap, Ey j cap plus Z k cap. We are taking the first surface over here, and this dA, if I am going to draw a normal on this dA, it is along the positive y-axis, and the area over here is Ex into dz. Since it is along positive y-axis, the vector will be plus j cap. I did the E dot dA, that is E into dA. I component, K component, if I am going to do the dot product, it will become 0. Only the J component is going to persist. So at what point we are determining this flux? We are determining this flux at this coordinate. What is the coordinate? That is Ey, x plus dy z, and the area vector is dx dz into j cap. When I am taking this surface, what is the difference is becoming? The difference is becoming that the area vector is having now the normal on the negative y-axis. So the vector over here is minus j cap. It is minus j cap. So it is my E dot dA2 is equal to Ey at the coordinates x comma y comma z into dx dz into minus j cap. Okay. So total E. We are talking only about these 2 surfaces. We are not talking about the rest of the surfaces right now. So let us do for these 2 surfaces only. So it is total E dot dA 1 plus E dot dA 2 is equal to Ey x comma y plus dy comma z into dz dx minus Ey x comma y comma z dz dx whole into j cap. Is the expression clear? Is the expression clear? Got it? Understood? You can put this one as equation number 3. So this one is the net amount of the flux which is emerging out from this surface. and from this surface. We are getting this surface as 1 and this surface as 2. So this one is the amount of the flux which is emerging out from this surface number 1 and from surface number 2. So if I am now going to check, suppose this one, this surface, means this is the surface which is emerging out of the board, and just opposite the surface which is entering into the board, we are taking these two surfaces. So in which direction the displacement is taking place? It is taking place along the positive x-axis, here along the positive x-axis, and there it is along negative x-axis. So what is the area vector over here? What is the area vector over here? It is along positive x-axis. Okay. So what is the area vector over here? That is dy dz. It is dy dz. Okay. So similarly we can write E dA3 plus E dA4. We are writing E dot dA3 and E dot dA4. We can write this one in this way. That is Ex at x plus dx comma y comma z minus Ex x y z into dy dz. I can write this one in this way. Just similarly, as we had written equation number 3, I can write this one in this way. Okay? Clear? So this one is equation number 4. And now this surface, that is the top surface which is in this direction, and this surface which is coming under this direction. Okay, this direction. So if I am naming this one as 5 and this one as 6, then EDA 5 plus EDA 6 is equal. Now in this direction the displacements are taking place, it is along the positive and negative z axis. It is along the positive and negative z axis. So it is Ez x comma y comma z plus dz minus Ez x comma y comma z dx dy. This is equation number 5. Just similarly we had written. Okay. So this one is the amount of the flux which is moving out through these two surfaces. This one is the amount of the flux which is moving out through this and that surface. And this one is the amount of the flux which is moving out through this and this surface. Okay. Okay. So total flux, that is phi, is equal to, I am going to add this equation number 3, equation number 4 and equation number 5. I am going to add it up. Okay. So I am going to add it up. I will get the total flux which is moving out throughout all these 6 surfaces. Right. So I am just adding it out. Ey x comma y plus dy comma z minus Ey x comma y comma z whole into dz dx plus E x plus dx y z minus Ex x comma y comma z into dy dz plus Ex x comma y z plus dz minus Ez x comma y comma z dx dy. So I have added up. These 3 we had added together. Okay. Fine. Now the divergence we have learned at the very beginning how to take out the divergence. Divergence is flux divided by the small volume. That small volume. Okay. So what is the volume of this cube? What is the volume of this cube? It is dx, dy, and dz. That is the volume of the cube. So the volume of this small cube, or you can write this one as d phi, you can say. The volume of this small cube is d phi divided by dv is equal to, I am dividing this delta expression by dx, dy, and dz. Dx, dy, and dz. So if I am going to divide this expression by dx, dy, dz, what is the part remaining? The remaining part is ey x comma y plus dy z minus ey into x comma y comma z divided by, if I am going to divide this one by dx, dy, dz, what is the part remaining? Ex, x plus dx, y z minus ex, x comma y comma z divided by dx. This is remaining. And if I am dividing the third one, so it is coming ez into x comma y comma z plus dz minus ez x comma y comma z divided by dz. This is remaining. This one is the part which is remaining. So if you see the first expression, that is electric field around x, y plus dy, means there is no change in the x and the z axis. There is no change in the electric field around x and the z axis divided by dz. So what we are getting by this entire expression? The entire expression speaks about this, that del E is equal to, this particular expression can be written in the partial differentiation format, because the change is only taking place along only one axis. It is not taking place along all the directions at a particular field. So it is del Ey by del y plus del Ex by del x plus del Ez by del z. So the divergence of E means, the term divergence of E means, it is the partial differentiation. It is the partial differentiation of the electric fields or electric field along x-axis, partial differentiation of the electric field along y-axis, and the partial differentiation of the electric field along z-axis. Okay, and this thing we had got to be as rho by epsilon naught. Okay, understood? So from here what we are learning, suppose this one is a surface. Direction. We are going to have a non-zero divergence, because what does this resemble? It resembles that there is a point source, there is a source from which the electric fields are radiating out. So there is a point source which is radiating out the electric field. So there is some charge inside that closed surface, and if there is a charge inside that closed surface, and if there is a charge which is there inside the closed surface, means it is having a surface charge density. It is having a surface charge density, because there is some charge which is emerging out, or which is producing some electric fields which are radiating outwards. So there is a source from where the electric fields are emerging out. So there is a value of rho, and if there is a value of rho, the divergence of electric field for that closed surface will be greater than 0. Now suppose if you are taking this type of surface, this one is a surface, and you are seeing that the electric fields are coming like this. Does this diagram replicate that there is some point charge inside it? No, it is showing that the electric fields are coming inside the point. Okay, so there is no source over here from where the electric fields are emerging out. Here the electric field lines are coming towards a point source, So the divergence, we can consider that there is a negative charge over here. We can take that this one is a negative charge over here, where the electric field lines from various things are coming out. coming into that. And suppose you are going to take this one is a surface. Some electric field lines are like this, some electric field lines are like this. It replicates that there is some charge which is emerging or some electric field in this direction. Okay? While there is some negative charge where the electric field is entering into the particular space or particular body. Okay? So why we did it is that the reason of doing it is that how we implicate the Gauss's theorem in order to prove the divergence of E is equal to rho by epsilon naught. Okay. So this one is basically the electrodynamics in which we find out that how the electric flux is producing or how we can determine the total amount of the electric flux about a closed surface. Okay. So today's class is over. Thank you everybody.